Going back to connected objects, let's say it's a small train. This is the engine. The mass of the engine is 100,000 kilograms. And these are two compartments. Let's say this one is 20,000 kilograms. And this one is 15,000 kilograms. And let's say the engine is accelerating at 0.5 meters per second square. If the engine is accelerating at 0.5 meters per second square, what is the driving force? What drives the engine forward? What is the driving force? Okay? And also find the tensions in the connecting links. So the question is, find the driving force and find the tensions in the links. So as I said earlier, what do you do for connector systems? Take one object at a time and then discuss the forces acting on it. That's not the end of it. There are some forces acting like frictional forces. There's a frictional force of 8,000 newtons acting on this. There's a frictional force of, obviously there are wheels, so I'm not drawing all those, 2,000 newtons. And there's a frictional force of 1,500 newtons. Okay. We'll go into friction later on in detail, but right now, let's say there's a flat friction that much. So what do? Go for forces acting on this object. First one, let's say the engine. What are the forces acting on it?
Weight.
The weight is acting downward. And there is the normal reaction acting on it upward. Those two are equal and opposite, so I'm not going to really draw them right now. Because the train is going this way, definitely not going up and down, right? So we are not really interested in the normal reaction at this point. At this point, forget about normal reaction. Even here there is a weight downward, there's a normal reaction upward. There's a weight downward, the normal reaction upward. The normal reaction will become important when you actually have to discover these forces yourself. Okay, till then, we'll just keep away from that part of it right now from the problem. So, what are the forces that are acting? Other than the normal force and the weight, what are the other forces acting? On this engine alone, force F pulling it forward. What else? There is 8,000 friction coming backward, and then tension. What is tension doing to this engine? Pulling it back. So how do you set up Newton's second law in this? Yes.
So is the 8,000 newtons the friction and the force going forward, are those a pair?
No, not at all. No. Not at all. This is 8,000 only for friction. Like how much drag? That has nothing to do with that. That's a driving force. So how do you set, now which way is the engine going? So which force is bigger? This side is bigger. So take the bigger minus the smaller ones. Minus 8,000 minus tension is equal to mass times acceleration. So 100,000 times 0.5. So your equation develops into 8,000 minus T is equal to 50,000. So F minus T is equal to 58,000. So that's an equation we have come up to right now. Now let's take the second object. Let me know if you have any questions at any point. Now let's take the second object. Again, we're not going to worry about downward and upward forces. What is the force that is pulling this one? Okay, if the other one, if the engine is accelerating at 0.5, this also is accelerating 0.5 because they're connected. What's the force pulling this that way? The tension, the same tension as that. And then 2000 is backward. And then again tension. Is this tension same as that?
Yes.
No.
What did I say about tension? Tension is the same in
Every connected line.
in every string or every cable in one link. If you have one string, throughout the string, the tension is the same. But this becomes a different one. So this is a different tension. Therefore, I have to now call this one as T1. And I have to call this one as T2. Because there are more than two strings, more than one string, so I have to now classify the tensions differently. All right, so that's tension T2, and everything is ready. So set up your equation. T1 is forward, that's obviously bigger, minus T2 minus 2000 is equal to 20,000 times 0.5. So you have T1 minus T2 is equal to 12,000. So we have this equation, keep it aside. Now let's go to the last one. The last one is being pulled forward with T2. And therefore the equation is T2 minus 1500 is equal to 15,000 times 0.5. That's also accelerating the same way. And so your equation is T2 is equal to 9,000 newtons. So we solve for T2 right there. We solve for T2. Now what do? Bring the T2 and substitute it here. You can get T1. So what is T1? T1 minus 9,000 is equal to 12,000. So T1 is equal to 21,000. And then put the T1 into this equation, we get F. So F minus 21,000 is equal to 58,000. So F is equal to 79,000. So the driving force that takes it forward at an acceleration of 0.5 meters per second square is 79,000. And we have discovered the tensions in the links also. Now, what is one thing that you can clearly see? Engine, first compartment, second, third, fourth. You can have many, right? In a train, you can have so many compartments. Now, where will the tension be greatest? In which link will the tension be greatest? Right next to the engine. That will have the greatest tension because you have so many compartments behind. The last one is supposed to have the least tension in the links. You get my point? Yeah.
So like in a wheel train, it's not like going by a rope. It's like the little metal things.
Yeah.
Is there still considered?
It's still the same thing, yeah. Even in the metal, it's like a chain. So it's a metal link like this. It's basically like hooked. So that's what it is holding it. So it's still, there's a pull and push. So it's the same thing like a rope. I mean, it's not a rope, but it is a link. So when you have a link, this link is pulling that in this direction, this one is pulling it in this direction. So just like T1, you can call it normal force, N1, N2. Yes?
When setting up the equation in like every problem, is like force just like the bigger force minus the smaller?
Yeah.
force?
That's the best way to go for.
And then if there's no tension, is it you just bigger minus the smaller? Because like in this, you do bigger minus smaller than the tension.
In this one, yeah. In this one, this side is bigger, this side is smaller. I mean, that is, so that there is a little logic that you're going to use there, And so when you use a little logic, the sign convention, you don't have to really worry much about. But yeah, there are some books actually take this as positive and that as negative, and all that stuff. So I've seen students making more mistakes in applying sign conventions and messing the whole thing up. Instead of that, you go by the real logic. Okay, it's going this way, so obviously these forces are bigger than this. Apply that way, the second law, and you'll be more successful there. Okay, questions? All right. The next concept is elevator. So let's say we have an elevator of mass 2,000 kilograms, including the passengers, and that's a cable that supports it. So the cable that lowers and raises the elevator is that one. Now, if the whole thing is not moving, at rest, if the elevator is at rest, what is the tension in this cable? If the elevator is at rest, what is the tension in the cable? Yeah.
It's 19.6.
So yes, mark the forces first of all. So the force acting on this one, the force acting on the elevator downward is the weight, which is 19,600 newtons. That's a weight. And the force upward is the tension of the cable. And what do you know about tension and the weight? It's at rest. So, at rest, if velocity is equal to 0, then tension is equal to 19,600. What law did you use to justify that? Yes.
Third law?
Huh?
Third law?
You always go from the back or what?
First.
The first law. The first law is what says if the net force is 0, then the object should be at rest or moving in constant velocity. You know that, right? Okay, so first law. According to first law, since it is at rest, these two should be equal. Yeah.
If you had two cables, would the tension be evenly distributed?
Where is the other cable?
So
If there were two cables going
Oh, just hooking up the same object?
yeah, would it be equally distributed?
Shared, yes. Yeah. Cables, you can have sharing of it. What if you have 100 cables? Divided among all of them. In other words, the total force downwards should be equal to the total force upwards. That's it. Okay? Now, if velocity is equal to 2 meters per second square upward, if this is moving upward with the velocity of 2 meters per second, 2 meters per second, what will be the tension? 19,600. Good. Why? No acceleration. Again, which law? First law. According to first law, if there is no acceleration, which means the object is at rest or moving with a constant velocity, the net force must be 0. So again, the two forces must be 0, which means whether it's going up or going down at 2 meters per second, no difference. You get it? That means if the elevator is like moving up at 2 meters per second or moving down at 2 meters per second, the tension is exactly the same as the weight. Remember all these little concepts when you start applying into different places. So Newton's first law is coming into action again. If there is an acceleration of 2 meters per second squared upward. Then, so if it is now accelerating of 2 meters per second squared, if it is accelerating at 2 meters per second square, which one must be bigger? This or this must be bigger? Tension. So you write the equation, tension minus 19,600 is equal to 2,000 times 2 MA. So 2,000 times 2. So tension is how much? 23? So the tension is actually 23,600 newtons, bigger than the weight. Obviously it has to be bigger in order to create that acceleration. Which law is this now? Second law. Yeah. That's the second law. Only when you talk about action-reaction pairs, identifying a pair, that's when third law comes in. Otherwise, second law. In this case, because it's accelerating, it's not first law. First law is zero acceleration. This one is some acceleration. What if acceleration is 2 meters per second squared downward? If it's accelerating at 2 meters per second squared downward, then equation, which one is bigger then? If it is accelerating downward, that will be bigger. And so if it is downward, then weight is bigger. 19,600 is bigger than tension by the same amount, 2,000 times 2. So tension is equal to how much? 15,600 newtons. That means if the elevator is on its way down, with an acceleration, the tension is actually lower than the weight of the elevator itself. So you can see how the tension is affected by something moving upward. So if you want to haul something up, there's a likely chance of the cable or the rope breaking because you're just holding. If you're holding something like that, lifting something like this, now there's a tension. If I start pulling it up, there's a chance that it snaps off. But if I'm lowering it, there's less likely to break. You understand? So if you're lowering something down, there's less chance of it snapping. But if you're trying to pull it upward, the tension goes to the higher end, more than the weight. So there's a chance of it breaking. Yeah.
What if you gradually raise it up?
What does gradual mean?
Like just
Yeah.
like I guess constant.
Yeah, I mean, if your acceleration is lower, then this will be lower. That's all. So if you make the acceleration instead of 2 meters per second square, make it 0.1 meters per second square, then obviously this tension is not significantly bigger than this. So, but you can start setting it into motion. What I'm trying to say is, if the acceleration is 2 meters per second square, it's a strong acceleration. So if like pulling it up quickly. Yeah. So questions about it? All right. Good. Now come back to the elevator again. And now you are inside the elevator. So we are not worried about the cable and stuff like that. We are only interested in this. That's you. That is you. So the object now is not the elevator, but the passenger in the elevator. Okay? The object is now the passenger in the elevator. So what happens to the passenger under the same situations? If velocity is 0, what are the forces acting on the passenger? Weight downward. Okay. Let's say. Let's say. Make it an even number. Okay. 100,
Then you got the other.
not me, 100. What is the force downward?
100.
980 newtons. 9.8 times 100. 980 newtons is the weight of the person. What is the other force acting? What do you call it? The normal reaction. And how much is that? So the normal reaction is equal to 980 newtons also if the velocity is 0. Okay, because the same reason, first law. What if the elevator is moving up or down with 2 meters per second, up or down? What's the normal reaction? 980 newtons. The same thing like last time. Instead of the tension, we're talking about the forces acting on the person only. What if it is accelerating upward at 2 meters per second squared? If the elevator is accelerating upward at 2 meters per second squared, what is the normal reaction? Is it supposed to be bigger or smaller than 980? Bigger, right? Because if it is accelerating upward at 2 meters per second squared, then NR is bigger than 980 by MA. So NR is equal to 1180 newtons. So the weight of the person is only 980, but the normal reaction is now 1180. That means the person feels a heavier force pushing his feet. The person feels a heavier force, a bigger force pushing on his feet upward. And that's the reason why you feel heavier. You feel heavier. It's a feeling. Okay? So when you actually press the elevator, you're going up. As soon as the elevator starts moving, you feel like heavy. What made you feel the heaviness is the normal reaction, not your weight. Your weight is still 980. But what you feel is a normal reaction. Okay, so you will feel heavier. Yes?
So like, what is it whenever you're like going up, you're taking off, and like you're trying to lift your feet up, it's harder to like have you ever done that before?
While the elevator is moving up?
While you're going up.
Because that's why I said, since you're moving upward, things are different. You can't, because it's accelerating upward, the elevator floor is coming with you. So therefore, to move something against it, you need to put more effort. Normal reaction is more. Your contact with the elevator is harder. Your contact with the elevator is harder. That's what gives you this. Now, if you're standing on a scale, imagine you put a scale over here and stand. You take your scale and put it in the elevator. The scale the pointer types, not the digital one. The digital one normally locks up after you stand, right? But the analog one, well, that can change according to the situation. So you stand on the scale, and if the elevator is accelerating upward, and you look down at the scale will read more. What does the scale measure? Normal reaction. The scale only measures the normal reaction. A scale never measures your weight. The scale will not measure your weight. The scale only measures the normal reaction. Okay? So standing on a scale doesn't mean it's supposed to read the weight. What if I'm standing on a scale like that? I'm standing on the scale, but I'm putting my hand here. Will it read my weight?
No.
No, because I'm taking some support here. So which means I'm not resting properly on the scale. So the normal reaction from the scale is less, and so it will read less. What if I hold from here like this? Yeah, you'll feel heavier. Like you can see that it is increasing. So the scale only reads the normal force. It does not read your weight. If you hold the scale in your hands and push it, then it will tell you how much you're pushing it by. So it will push you back, and that is what is being recorded. So the scale will read 1180 newtons if it's a Newton scale. Normally those scales are actually measuring in newtons, but it's calibrated in kilograms for you to read it right. Okay? So if the 100 kilogram person stands on it, it will go to a certain spot where it's actually 980 newtons, but it is written as 100 there. Now, if acceleration is downward 2 meters per second squared, how much is the normal reaction? So how do you find it out? If it is accelerating downward, if it's accelerating downward at 2 meters per second squared, which is bigger? 980 is bigger. So therefore, 980 minus NR is equal to 100 times 2. So NR is equal to 780 newtons. So the normal reaction is reduced, and so you feel lighter. So when you're on the 20th floor and you push the down button, initially you'll feel kind of light as soon as it takes off. Yeah.
Since there's more force when you're going up, there's more force pushing on your feet, so you feel heavier. Does that mean when you can jump higher because there's more force pushing you back?
When, in which case? In this case?
Yeah.
Well, higher with respect to the outside, not with respect to the elevator. With respect to the elevator, whatever you apply extra on the floor is what it applies back on you.
Yeah, so you could jump. So like if I were to jump right now, I would get like
No, but this extra force that's coming in is for the acceleration part of it. Beyond that, if you want to take off, then you need to put in whatever extra contribution you do. That is what helps you. You can't take the benefit of the acceleration of the elevator itself. Is this part clear so far? Yes.
So the normal reaction is going up, but why is that making you be heavier? Like
In this case,
yeah.
because the whole acceleration is upward. When the acceleration is upward, this must be bigger than this. That is what. See, you as an object, if the elevator is accelerating upward, you are also accelerating upward. How can you, as an object, accelerate? According to Newton's second law, if you're accelerating, the net force must be upward. You get it?
I get that.
Mhm.
Why does it? So is it harder to accelerate more because you're already accelerating? Like
Oh, to take off from the floor?
Like
Is that what
why,
he's
why are
saying?
you heavier?
Because NR, normal reaction, is what measures what gives you the feeling of heaviness. You are not heavier. You are exactly the same. You are always 980. But it's only a feeling. As I said, it's a feeling. And what is the thing that gives you the feeling that you're heavy? It's a normal reaction. If the normal reaction is less, the feeling is also going to be less force. Yeah.
Is that 1189, is that respect to the elevator or respect to the ground?
elevator.
Like 1180 newtons?
1180 Newton is the normal reaction, the actual force exerted by the floor of the elevator on your feet.
Okay.
Okay, any questions? You may have lots of questions as we go on. So, ask. So when it is accelerating upward, NR must be bigger than this. If you're accelerating downward, NR will be lower than this. Yes?
Well, so like when we're dealing with acceleration, like when we're pointing downward, will the downward force always be bigger than the
Yes.
downward?
Mhm.
Just like making sure.
Yeah. Because this object, the overall acceleration is downward, which means the overall force must be downward. There are only two forces acting. There are only two forces acting. One is the weight, the other is normal force. If the net force is to be downward, then this has to be bigger than this. Which in other words means NR must be smaller than this. Yes?
So since the net force when you're like going up in the elevator, the net force is the
Upward.
NR is bigger. But if NR is going up, then why does that make you like? If NR is going up, why would that make you feel heavier?
That's exactly what I'm saying. What gives you the feeling of weight is not your weight, but the normal force. Okay, one more step and then you'll answer that question yourself. One more. Now let's say the elevator cable breaks.
It's not like
Let's say the elevator cable is broken. And as soon as the elevator cable breaks, what's going to happen to these two forces? Let's find out. Let's find out these two. If the elevator is breaking, what's going to be the acceleration? That's the acceleration, right? Now how do you set up the equation again? 980 minus nr is equal to 100 times the acceleration that you're going through. So what is nr equal to? 0. What does that mean? That means the floor of the elevator is not contacting you, not making contact with you at all.
Is that just because of a specific weight? Or is that for
It's in all cases.
So what? No.
Whoever is there will experience the same effect.
Oh yeah.
It changes the digits down based on his weight too.
So the elevator is coming down with 9.8. You're also going down with 9.8, right?
Yes.
So since the acceleration is 9.8 meters per second square, the normal reaction technically is 0. Because the net force is 980, which means nr is 0. When nr is 0, that means you are literally not making contact with the ground. So how much do you feel? You'll feel nothing. You'll be like weightless. That is called weightlessness. That condition is called weightlessness. Weightlessness is not a condition where there is no weight acting on you. That's wrong. Write down what is weightlessness. Weightlessness is when only one force is acting on you, that is your weight. The weightlessness, condition of weightlessness, is when only one force is acting on you, and that is your weight. Right now, why are we not experiencing weightlessness? Because the normal reaction is pushing us up and reminding you that you're heavy, you're heavy, you're heavy. All right? The normal reaction is what is reminding you about it. Now, if the normal reaction is 0, suddenly you feel like, I'm not heavy at all. But is there weight still acting on you? Yes, very much. So when only one force is acting on you, which is the weight, that condition is called weightlessness. Can you experience weightlessness? Yeah, jump off from the building, you'll experience weightlessness. And what about here? Inside the elevator, you can experience weightlessness. The same weightlessness condition that people in space experience, you can experience inside the elevator. In other words, what? If you push the floor of the elevator, you'll start moving up to the top. You know what I'm saying? You will feel the zero gravity effect inside the elevator, only for a short time though, yes.
Is that how that plane works? Like the plane?
The plane, yeah, the plane, I told you about my son, going, the plane was actually going not vertically down, because that's technically not, practically not an easy thing to do. Huh?
Not smart.
That's not a smart thing to do, going like this, because then you won't be able to recover at all. So what they do is they go like this at 30-degree angle. They go like this at 30-degree angle
Did your son do that?
at an acceleration of 19.6 meters per second square. They go, going like this. So what is this component of that acceleration?
Weight G
Sine 19.6.
Which is 9.8. You ever get it? So the plane goes up sufficient height and then goes at an angle of 30 degrees, but the jets are in full operation and it is accelerating at 19.6. So it accelerates at 19.6 and goes down like this, creating the vertical acceleration to be exactly 9.8, so you experience the same thing. Yes?
I had time this weekend in my flight. hold it, I'll get a video of me holding the pencil and like going down because it'll actually like.
It
go down.
tosses up, exactly.
You don't actually, it's one on the throttle.
Yeah.
It's not.
Like, is there like a point where like you get weightlessness and then like it's just the same, or because of like
No, I mean till it takes off. In fact, the plane goes like this. It goes at 30-degree angle like this, creating the 9.8, and then it goes like this at 19.6.
no, I just mean like let's say you jump off a building, but like jump off a 2-story building or like a 50-story building. Like, is the weightlessness?
Well, let me explain to you. You won't experience perfect weightlessness when you jump off a building, so don't try it.
Air resistance.
All right? Why? Why?
Air resistance.
Air resistance. So air resistance is a force that kind of reminds you that you have something going on. And so you won't feel exact weightlessness condition. The weightlessness condition is when there's nothing else but only one force acting on you, which is your weight. Yeah.
Or if you were in a box and you jumped out of the building.
But the box is where you suffer air resistance.
Like a box, like an elevator.
No. Now this elevator is not going to come down with 9.8, never. It will never come down to 9.8. Yeah, initially it might, but later on air resistance builds up and so it won't accelerate at 9.8 at all. So, well, if you forget about air resistance, then it's yes.
If you were falling in a big enough elevator, you had a big boulder, and you threw it, would you go back?
Oh yeah, the same thing as.
Why is the boulder, if you were falling in an elevator, you threw a rock forward?
Yeah, I mean, you throw anything, you're supposed to be moving backward, inside there, because you're not moving. That's why I said, as the elevator is going down, if you push a little bit on the floor, then it'll take you upward to the top of the elevator. And then if you push from the top, then you come down. So you're literally experiencing weightlessness, pure weightlessness. And that's exactly what you'll experience in this motion. But then when you do this, it's going to be 2G.
You'd be stuck to the ground.
Yeah, it'll be 2G. That's what my son tried to do push-ups when it was 2G. It was so tough. In fact, he didn't expect the weight. He pulled himself up. He pulled himself up because imagine two people are sitting. Imagine a person is lying down on him exactly the same weight as him. That's how it will feel. You understand? That's exactly the feeling. So he told me that it is just exactly like as if I'm carrying somebody above. He can normally do a lot of push-ups, but that one, he just pulled himself up with a lot of difficulty, and then he wanted to take a second one. So he was trying to go down, but he just collapsed on the floor. He just collapsed because he couldn't control the way it was going down. Because it is 2G, it was too fast. So he literally almost banged his head on the floor. Yes.
Why is your son playing like this?
Imagine this is one wall, and this is the other wall, or a pole, post, or whatever. And imagine there is a, don't draw it right now, don't draw it. Imagine there's a rope like that. Imagine a rope is pulled from one side to the other side. And imagine like you hang from the middle. So when you hang from the middle, what happens is the rope goes like this, and like this, and you'll be hanging from there. Now when I say hanging by your hands, okay? Not hanging by your neck. So that is you. Or let's say it's an object. Let's say it's an object of mass. Okay, so that's 100 kilograms. All right, let's put 100 kilograms in there. So if you have 100 kilograms in here, and this whole thing is hanging, and if this angle is 20 degrees, if the angle is 20 degrees, and you are actually right in the middle. What are the tensions in these cables? What are the tensions in those ropes? Okay.
Wait, are those two different ropes or one rope connected?
For the time being, these are two different ropes because this is a knot in between.
It's not like a flip that you're just pulling it down. It's a knife.
Yeah, a knot means it's a branch. So whenever there's a branch, now you can't consider that to be the same. So this is 100 kilograms. Let's find out the force acting on this. Forces. One is 980 newtons acting straight down. What's the other? The tension here. How much is the tension when the whole thing is still? What tells you that? What law?
First law.
First law. So the tension there is 980. Now let's go to the knot. Let's go to the knot. There's no other object, right? There's no other object. Go to the knot. The knot is acted on by how many forces?
3.
3. What is the force downward? T, which is? So from here to here is one string, so that has to have 980. So this knot is being pulled down with 980. And the knot is being pulled in this direction with a force T1. We don't know. This knot is also pulled in this direction with T2. We don't know.
But aren't they equal?
We don't know.
Because they're different ropes.
You cannot guess anything. It may be equal, but you cannot guess. Now, the knot is in equilibrium. What is the meaning of that?
Net force is 0.
Net force is 0.
Good job.
The net force is 0. The knot is in equilibrium because the net force is 0. Newton's first law again. Although there is no object over there, the net force is 0, so the knot is still. Right? So since the knot is in equilibrium,
T2 plus T1.
what is the condition for equilibrium? Conditions for equilibrium. Net force in the x direction must be 0, and the net force in the y direction alone must be 0 also. Because if the net force is 0, it won't have an x component or y component. So what we do now is we have to resolve. There are 3 forces acting on it. So we're going by method of resolving. So here is a method of resolving. That's our axis. 980 is acting straight down. This one is acting that way. This one is acting this way. And you know this angle is 20 degrees. That is 20 degrees. So let's split it and make a table. X and Y. So what are the X components of this? 0. And Y component?
Negative.
Negative 980. Always before you decide, just think is downward or upward. It's positive, negative. Very common mistake, forgetting about that. You're done with this. Now go to this one. This one has 2 components. Where are the 2 components? One is here, and the other is this way. What is this component? Horizontal component. T1 cosine 20. Positive. What is this component? T1 sine 20. Now go to this one and split it the same way. What is this component? Negative T2 cosine 20. And this is T2 sine 20. And the total of this is T1 cosine 20 minus T2 cosine 20. And the total of that is T1 sine 20 plus T2 sine 20 minus 980. That's the total there.
Why would the T1, T2 sine 20s not be negative? It's like the rope on the
This one?
Yeah.
Both are going upward. The vertical component of this is both upward.
But not negative from the
These are the two components. One is this component, which is negative along the negative x-axis, but this is along the positive y-axis.
yeah. If you're going the other 20, wouldn't it be?
Which 20?
No, it's still upward.
It's still be upwards.
We are looking at the force T2,
Versus
not
one.
this one.
Okay.
We are looking at what is T2 doing to the knot. What is T2 doing to the knot is what we are concerned about. Not this. You get so far?
Yes.
And then apply these conditions. Net force in the x direction must be 0, which means this must be 0. So T1 cosine 20 minus T2 cosine 20 should be equal to 0, which means T1 cosine 20 is equal to T2 cosine 20. Now cosine 20 is gone. T1 is equal to? Proved. So we are not taking anything for granted. If it comes up mathematically as a proof, then accept it. So T1 and T2 are exactly the same.
So when making a chart like x and y,
Mhm.
so the 0 and then the negative 90, they refer to the knot like going down,
The force that is acting on the knot going
Okay.
downward, yes.
and then the
These are all forces going from the knot. It's always from the knot. The knot is in equilibrium.
that makes sense.
Okay.
I got it.
You can call it horizontal and vertical, it's the same thing. I think you're familiar with both.
What if
Yeah.
the knot wasn't in equilibrium?
Say it again,
What if the knot was not in equilibrium?
then it will accelerate. It
So
won't be
would
staying
that mean,
still.
like, if one side is equal,
If it's not in equilibrium,
yeah, well,
then it won't stay in that position. It has to now swing and go somewhere else. But if it's going to settle somewhere, yes. If it is not in equilibrium, then it is not going to stay here. Say, for example, if the rope is too weak, what will happen is you're going to fall straight down. So if it is not in equilibrium, it's supposed to accelerate. But if no movement is taking place, that means that's in equilibrium. So you're using Newton's first law here, equilibrium. Equilibrium is first law. And what is the equilibrium? When an object is not moving or moving with constant velocity. And so in this case, this knot is not moving. This object is not moving. So we apply Newton's first law to both situations. We got this. So we know T1 and T2 are exactly the same. So what do you do now? Go to this one. T1 sine 20 plus T2 sine 20 is equal to 980 because it's equal to 0. Now since T1 and T2 are exactly the same, I can call it 2T1 sine 20 is equal to 980. Can you find T1?
Yeah, it's 536.
How much?
536.
536 newtons. It should be much more than that.
153.
No.
Much more than that.
No, it was.
536.
Is it still?
We
Wow.
had a 1432.
You just
Well, they're dividing it.
don't you just divide by sine 20?
You divide by 2.
And there's a 2 also.
It's 1432.
You're in agreement.
That looks more likely.
Oh yeah, probably radians.
I degree.
142.
How much?
432.66.
1
Yeah,
4.
that'll do it.
3-2.
Yeah, that's something you should be careful. 1,432 newtons on this rope. And what about this one? Also 1,432.
That's a lot.
And what is actually hanging is only 980.
1432.
Good job.
What is hanging over here is only 980. So the forces in these cables is much more than the weight of the object.
Because they're at an angle.
because of the angle. Well, that brings us to, let me give you a practical scenario where this can be applied. Imagine there is a, listen up, imagine there is a box or something that you need to carry. Okay, it's a small object, but it is something that you need to carry. Well, imagine the force, the weight of the object is 100 kilograms. So how do you want to transport it? Now there are two ways of transporting it. See, here it is. That is the object. There are two ways of transporting it. And so it's got a handle here. The two ways of transporting it is, one, tie a rope to it, pass a rope through inside. You pull from here and your friend will pull from there. You got my point? You got my point? So you're tying a rope through the object and you pull this rope and your friend pulls the rope, so this mass is off the floor, then you just go with it. Is that okay?
That'd be super heavy. It'd be way heavier.
Each person will have to bear this much force. If you're doing that, each person will bear that much force if the angle is 20 though, okay? Now, but the weight of the object is only 980. So in other words, one person can apply a force straight up and carry it by himself. When he's taking the help of another person and tying a rope like that, it makes things worse. You get my point?
Yeah.
Now the other option is, yeah, pass a pole through it, and then you carry from here and your friend carries from there. So you're going to carry from here and your friend carries from there. How much will each one apply? 490. So 490 here and 490 there. So you're sharing the thing. You get it? You're just sharing the forces because you're applying it vertically. So what I'm trying to say is this: when you apply the force at an angle, only a component of what you're applying is actually lifting the object. The rest of it is like you're fighting with your friend. This force is purely useless because you're pulling it like this and your friend is pulling it the other way around. There is no benefit. Yes.
Is that assuming that the case would be at the center of gravity on the plane? Would that person?
Oh yeah, then it'll be different. Yeah. Yeah, then things are going to be different. If the center of gravity, if the pole, now the pole is not our main object here. The main object is this one. Now this is something that you can actually use for the good as well. Now look, let's say your car got stuck somewhere into a wet soil or some slush. The car got stuck there. Now the car is not able to come out by itself. So here is the car. The car is here and it's got stuck and you're not able to carry it all by yourself because not carry it, move it out of the place by yourself. Engine is not helping it. So tying a rope there and pulling it is one option. Well, that's not going to work because if you pull it, how much can you apply? Your own weight.
Oh, I got it.
Your own weight is maximum you can apply, right?
No.
If you hang on something, then maximum you can apply is your weight. You can't pull it too much, all right? So what happens here is without anybody's help, you can still take the car out of this place. What you have to do is this. You have it?
It's something to do with if you tie it to like another like solid object.
That is right. You take a rope, tie it from the car as tight as you can onto a tree or anything solid on the ground. So that's a car. Tie it as tight as you can onto a tree like this. And then what you do, you go to the middle and push the rope like that. So what you're doing is exactly this. You see this? What you're doing is exactly this. When you push from here, the tension here and here will be extremely large compared to the force that you apply. These forces are going to be much greater. Of course, it depends on how much angle is involved. That's why I said you must tie it as tight as possible initially. So you can actually produce a tension in this rope far greater than what you're applying. And therefore the car can start coming. Car can start coming. When you get into trouble, you try it. Now, what if you do this? Tie from here to another tree. And then you walk this way.
Even duration.
It's actually going to, keep adding.
Like a little, circle here.
But again, there's a problem here. That is, the moment you start moving it, this angle will start decreasing. When the angle decreases, tension will come down. The angle is a very important thing. So you can't just do this forever like that. So, but yes, there is a multiplication factor coming in there. Yes.
What's the greatest angle to what's the maximum angle to obtain?
No, 0 degree is when you can get the maximum. All right, now let's say this angle is 2 degrees.
Oh boy.
It's a lot.
Now tell me how much is going to be here. So if it is 2 degrees, everything else is right, except this, it will be 2 degrees. Huh?
41,000.
14,000.
I don't know. Just work it out. I don't think so. I don't think 14,000. Check it out and see. 980 divided by 2 and then divided by sine 2. Is it?
14040.
Oh,
6.
just imagine how much force is
How
it.
many pounds is it? How much do you divide by?
If you divide by 9.8, you get the kilograms, then multiply by 2.2 to get pounds.
3,100.
So you can apply a much larger force when you can. So this is one of the reasons why if I give you a steel wire and tell you to break it, you can't break it. The steel wire, pull it as much as you can, and you won't be able to break it. What's the easy way to break it? Tie it between two supports. Tie it on that door, tie it on this door as much as you can. Hold the middle or call a little child and just ask the child to pull the steel wire and the wire will snap.
What?
Yes.
What happens in what would happen in like a tug of war? Like a tug of war, something comes and pushes them in. But they both
Oh yeah. That will cause a big difference.
Okay, can you explain?
Okay. One more situation here. All right, this box is resting on the floor. Let's say the box weighs 10 kilograms. The box weighs 10 kilograms. And suppose you tie a rope onto it and pull it like this. You're pulling the object in that direction. You're pulling the object in that direction with a force of 40 newtons at an angle of 30 degrees. Yeah, let's say it's frictionless.